Hello, and today we're going to learn a little bit about balancing chemical reactions. Now let's say that we are posed a question about the decomposition of ammonium dichromate, where it asks how many milliliters of water are produced from 46 grams of ammonium dichromate. Well, the first thing we need to do is we need to balance the equation. And when we balance the equation, we need to work on making sure that both sides of the yield sign have the same number of atoms for each element. And the only way we can do this is by adding coefficients. Now there's a couple different ways of going about balancing chemical reactions. The way that I find works best for a lot of people, myself included, is the guess and check method. So I'll run through that for now. So we want to look at our reactants and products element by element and determine how many we have on each side of the yield sign. So there's a couple different methods for how you can actually go about doing this. Normally I would recommend going with elements that are only in one compound on each side of your yield sign first, as that normally makes things a little bit easier. And for this one, we're going to go ahead and start off with nitrogen. So if we look here, we can see that for nitrogen we have 1 written right there, but it's in the parentheses as well. So we're going to have to do the 1 times the 2, and that'll give us 2 nitrogens for the reactant side. On the product side, we have N2, so that's going to be 2 nitrogens. So that one's good. So we'll move on to hydrogen. Now for hydrogen, we have 4 hydrogens on our NH4, but again, that's in the parentheses, so we're going to have to multiply that by that 2 subscript. So we'll have 4 times 2, giving us a total of 8. And then, when we look on the product side, we can see that we have H2O, which only has 2 hydrogens. So what we need to do is we need to add a coefficient so that those numbers will be equal to each other. So if I put a 4 in front of water, then my 2 will now become 8. Now whenever you add a coefficient, you have to make sure you do it for all the respective elements that are affected by it. We haven't done oxygen yet, so we don't have to worry about it right now. But now our hydrogens are balanced, so now we're going to move on to our next element. So I want to look at chromium. For chromium, we have 2 on the reactant side, and then for our chromate oxide, we have 2 on there as well. So both the reactants and products have 2 chromiums. And then finally, we're going to look at oxygen, where with oxygen we have 7 from our ammonium dichromate. And then on the product side, we have 3 from our chromium oxide. And then we have our 4 coefficient times 1 for the water. So we have 3 from the chromium oxide, 4 from the waters, and those added together is equal to 7. So these are equal as well. And so now all of our elements are the same on both the reactant side and the product side. So now this reaction is balanced. So now that we have our balanced reaction, we can go ahead and try to answer this question. So we're trying to figure out how many milliliters of water are produced from 46 grams of ammonium dichromate. We're going to go and start off with our grams of ammonium dichromate being 46. Then we're going to look at the periodic table and figure out the molar mass of ammonium dichromate, which you should calculate to be out 252.084 grams, with significance down to the 8. And that is going to be for every 1 mole of ammonium dichromate. Now that we are in moles of ammonium dichromate, we can go back and look at our chemical reaction. We can see for every 1 ammonium dichromate, we are going to make 4 waters. And so now we can get to our desired species of water. So again, we'll do 1 mole of ammonium dichromate for every 4 moles of water. Then we can look at the periodic table and figure out the molar mass of water. So for every 1 mole of water, we're going to have 18.016 grams of water. And then finally we can do a conversion from grams to milliliters. At room temperature, at sea level, 1 gram of water is equal to 1 milliliter of water. And so now we've reached our final unit of interest, and we can go ahead and multiply everything on top and divide by everything on bottom. So we'll do 46 times 4 times 18.016, and then divide by 252.084, and we will get an answer of 13.1501563 milliliters of water. If we look at our significant figures, we have 2 from the 46, 5 from the molar mass of ammonium dichromate. Our mole-to-mole ratio is an exact equality, so that's not going to limit us. And then 4 from the molar mass of water. So this will leave us with only 2 significant figures coming from the amount of ammonium dichromate. And so our final answer will be 13 milliliters of water. So now we're going to go ahead and take a look at this experiment in its full form.
There it goes. Okay. All right, and I'll give it just a little bit to make sure it really gets going. We'll hold this up here so that keep things a little bit contained. It's about to get started. All right, I think we're good. Hope I don't stuff it. All right, I might still keep going for a little bit. I'll turn the lights back on. So what do y'all think? Pretty cool? Yeah? All right, chemistry volcano, right? No oxygen needed. Pretty cool. All right, so
one thing you may have noticed during that decomposition of ammonium dichromate is that we went from a very bright orange powder to a very dull green, fluffy powder. And a large portion of that is due to the oxidation number of chromium changing from a +6 to a +3. And being able to figure out oxidation numbers is another method for balancing chemical reactions. For this one, we'll be balancing with electrons. And to balance with electrons, first thing I want to do is figure out all the oxidation numbers of each of the elements of the unbalanced equation. Then what we can do is we can write down both half reactions, the oxidation and reduction half reactions. Then we will make the number of electrons for both half reactions equal to each other. And using that information, we can normally get started on writing the coefficients for our reaction, but we may be left with some holes, in which case you'll want to balance like normal, where we're going to make the number of atoms of each element on both sides of the reaction equal to each other. And so let's go ahead and go through an example of this, where we have acetylene, C2H2, plus oxygen, O2, yielding carbon dioxide, CO2, and water, H2O. So the first thing we're going to want to do is we're going to write out the oxidation numbers of each of these elements. So for the acetylene, the C2H2, we know that hydrogen is going to have a +1 because it's bonded to a nonmetal. And so this is going to make each of the carbons have a -1 oxidation number. Then we go over to oxygen. It's in its elemental form, so it's going to be 0. Then we can go to carbon dioxide, where oxygen normally has a -2 oxidation number. And so we can do -2 times 2, giving us -4. And the carbon's going to have to be a +4 to give us that overall neutral charge of 0. Then we can go over to water, and water is going to have a -2 on the oxygen, like normal. And hydrogen is going to have a +1 since it's bonded to a nonmetal. And that gives an overall neutral charge of 0 when we multiply those out. So now that we know our oxidation numbers, we can go through and figure out which oxidation numbers changed. So looking at the carbon here, we go from a -1 oxidation state to a +4 oxidation state. And so we know that one changes, and the other one that changes is this oxygen going from a 0 to a -2 for both of these compounds in the products. And so with that, we can go ahead and start writing out our half reactions. So we'll do the one for carbon first. So normally whenever you have a carbon molecule and the oxidation numbers are changing, I would highly recommend that you leave all your carbons together, since normally it's a long chain. And so in this case, we're going to write our C2 for our carbon and write the overall charge for both carbons combined. So this would be a C2 to the 2 negative. Then on the other side, we're going to write our C4 plus, but we need to keep in mind that for our half reactions, we still need to keep things balanced. So we're going to add a 2 coefficient over here to make sure that we have our 2 carbons matching with our reactant side. So at this point, we need to figure out where our electrons are going to go. So on the reactant side, we have a -2 charge. On the product side, we have 2 times 4 plus, giving us a +8 charge. And so this is a difference of 10. So we're going to need to add 10 electrons to the product side so that both sides are equal to a -2 charge. So this is our oxidation half reaction. And now we're going to look at the oxygen. So for the oxygen, we have O2. And then on the product side, we need to go ahead and have our O2 minus, but again, we need to put a 2 coefficient in front of that so that our oxygens are balanced. So again, for half reactions, it's pretty straightforward since normally you're just dealing with one element, but you still have to make sure it's balanced, otherwise that will really throw you off. Then what we need to do is we need to figure out where our electrons need to go and how many we need to add. So on the reactant side, we have a 0 charge. And on the product side, we have 2 times -2, giving us a -4 charge. And so we're going to need to add 4 electrons to the reactant side. And this will give us our reduction half reaction. So now that we have both sets of our half reactions done, we can focus on these 10 electrons on this side and our 4 electrons over here. And we need to figure out what is the lowest common multiple between these two. And that number will come out to be 20. And we can have 10 times 2 to give us 20. And we can have 4 times 5 to give us 20. So basically what we're going to do is now we're going to take these half reactions and we're going to multiply it by the numbers they need to get to that lowest common multiple. So we're going to multiply everything in this upper reaction by 2, and we're going to multiply everything in the reduction half reaction by 5. And so when we do that, we're going to end up with 2C2 to the 2 minus, and then 2 times 2 giving us 4C, 4 plus 20 electrons. And then for the reduction half reaction, we're going to have 5O2 plus 20 electrons, and then the 5 times 2 giving us 10 O2 minuses. So at this point, we should be good to go ahead and balance our original reaction. So if we look at the 2 here for that C2 2 minus, that correlates with the acetylene. So we're going to just put a 2 coefficient in front of the acetylene. Then we can look at the 4 C4 plus, and that's going to correlate with our CO2. So we're going to put a 4 in front of CO2. Now we can look at the other half reaction where we have 5O2. So that correlates with the O2. So we'll put 5 there. And now we're left with one more blank that we don't know. And here we have 10 O2 minuses, but that's split among 2 different molecules on the product side. So there's a couple ways of going about doing this. We could look at the 4 CO2, realize that we have 8 oxygens coming from there, and then know that we need the remaining 2 oxygens on the water. Or the other way you could do it is balance like normal and look at your hydrogens and say that we have a 2 coefficient here, 2 hydrogens in each of those, so 4 hydrogens total. Since we have 2 hydrogens over here, we need to multiply this by 2 to get up to 4 hydrogens each. Either way will work. It is whatever your preference is on what makes sense to you. And so that's how we can balance this reaction. Now I want to go ahead and go through another example to help highlight some other points on this. So if we look at the reaction of water plus potassium permanganate plus potassium iodide yielding manganese oxide, iodide, and potassium hydroxide, we can go through and write down all the oxidation numbers for each of these elements. So for the water again, we get a -2 for the oxygens and a +1 for the hydrogens. For the potassium permanganate, we have potassium, which is a group 1 metal, so that's going to be +1. We have oxygen, which is going to be a -2. You may have also recognized this as a polyatomic ion, which would be a fine way of doing this as well. Or we just have one variable here and we know it has to equal a charge of 0. So we can say we have a +1 from the potassium. We have -2 times 4, giving us -8 for the oxygens. Those added together gives us a -7. And now we need to get to 0. So manganese has to be a +7 in order for that to be true. So +7 for manganese. Then we look at potassium iodide. Potassium being a group 1 metal is going to be a +1. The iodide being a halogen or in group 7 is going to be a -1. Looking at the manganese oxide, the oxygen is going to be a -2. It's overall neutral compound. So -2 times 4 for the oxygens gives us a -4. So the manganese has to be a +4 to keep it neutral. Then we have iodine and its elemental form, so it's going to be 0. Then we have potassium hydroxide. The potassium is a group 1 metal, so it's going to be a +1. Oxygen is normally a -2. And then hydrogen can either balance it out to 0, or we can say it's bonded with a nonmetal, such as oxygen, for a +1. Alright, so now that we have all of our oxidation numbers done, we need to look and see which ones are changing. And so if we look through here, we can see that our manganese is changing from a +7 to a +4. And then we also have our iodine going from a -1 to a 0. And so those are going to be our two half reactions. I'll go and start off with the manganese. So for our manganese, we have going from a 7 plus to manganese 4 plus. And so now we need to figure out where our electrons are going to go and how many we need to add. So on the reactant side, we have a positive 7. On the product side, we have a positive 4. So if we add 3 electrons to the reactant side, that'll give us a positive 4 on both sides. All right, and so that would be our reduction half reaction. Now we're going to look at the iodine. So again, similar to the last one, since we have to have I2 here, we're going to have to put a coefficient of 2 in front of the I minus. Again, make sure your half reactions are balanced. So we have a 2I minus becoming I2. So now we have a negative 2 charge on the reactant side and a neutral charge on the product side. So we're going to add 2 electrons to the product side. So now that we have both of our half reactions, we need to figure out what is the lowest common multiple between 3 electrons and 2 electrons. And that would be 6. And so now we can multiply the half reactions to equal 6 electrons. So we're going to multiply this reduction half reaction by 2. And we're going to multiply the oxidation half reaction by 3. Alright, once we do that, if we look at the manganese, we'll get 2 Mn7 plus 6 electrons, yielding 2 Mn4 plus. And then for the other reaction, we're going to have 3 times 2, giving us 6 I minus, yielding 3 I2 plus 6 electrons. And so now at this point, we can go ahead and start filling in some of the blanks on our overall reaction. And so we can look at our manganese here. We have 2 of them, so I'm going to put a 2 in front of the KMnO4. And then we also have a 2 on the Mn4 plus, so we can put a 2 in front of the manganese oxide. All right, now we can look at our iodine here. We have 6I minus, so that's going to be a 6 in front of the potassium iodide. And then we have a 3I2, which is just going to be a 3 in front of our I2. So now we have 4 of the coefficients figured out. We still have 2 more blanks. And at this point, this is where you have to orchestrate the balance like normal. But since we only have 2 blanks, this can be a little bit easier, especially if you kind of choose things strategically. So if we look at our reactant side, we can see that we have all the potassiums accounted for. We have 2 potassiums from the potassium permanganate, 6 potassiums from the potassium iodide, giving us a total of 8 potassiums. And the only place with potassium is this potassium hydroxide. So we'd have to multiply this by 8 to get the potassiums to be balanced. Now at this point we could choose oxygen if we wanted. Oxygen is in 2 of the reactants and 2 of the products, so that one's maybe a little bit more tricky or has a little bit more math. Or we could choose hydrogen, where we know the exact number of hydrogens being this 8 coefficient times 1 here, giving us 8 hydrogens in total. This one's going to have 2 hydrogens each, and so if we multiply this by 4, that will give us 8 hydrogens. Then we can go through and double check our last element, the oxygens. We'll have 4 times 1, giving us 4. We'll have 2 times 4, giving us 8, so 12 in total. And then we can do 2 times 2, giving us 4, and 8 times 1, giving us 8, for 12 in total, so 12 on both sides, meaning the whole thing is balanced. So again, most people work really well with the guess and check method, but balancing with electrons is a really good go-to if you're having a little bit of trouble. Anyway, I hope you found this useful, and I look forward to seeing you in the next video.